So what I want to talk about today with you is how we can try to understand and mitigate this issue of triggered earthquakes. Frequently, and probably most familiarly for all of you, you've heard the term induced earthquake. There's a slight jargon difference between induced and triggered, but for the purpose of this meeting, we'll just consider them the same, and I will probably say triggered instead of induced. It's just a habit of mine. So when I say triggered, I'm meaning earthquakes caused by fluid injection. So before I get too much into the details of how we might manage and mitigate this risk associated with triggered earthquakes, I just want to step back and talk to you about natural earthquakes first. So for natural earthquakes, we can estimate the amount of hazard and the amount of risk. The way this is done is by taking the hazard, combining it with the vulnerability in an area in order to determine the risk. Sorry if you can't hear me. So specifically, earthquake hazard is the probability of a specific level of ground shaking occurring due to an earthquake. And the vulnerability is the potential loss from that ground shaking, and it's often very much scaled with exposure. Exposure being things like the population that's in the area, as well as structure and infrastructure, and I'll go into more detail with that. So just as examples of how these things might be represented or measured, the United States Geological Survey comes out with a national seismic hazard map every 7-8 years, I believe. And the figure on the left here is the current version of the National Seismic Hazard Map. So these types of hazards are based on fault locations, earthquake history, and potential ground shaking in specific locations. And these are things that we can quantify. Whereas vulnerability is generally based on population density and the types of structures and infrastructures in an area. So now we know that fluid injection can trigger earthquakes, and from a scientific standpoint, this is fascinating. People have the ability to cause earthquakes. We don't want to, but we can. But what's important to understand in this context is how are they triggered, to what extent might they be triggered, and what can we do about it? Rick showed this slide in his presentation, and I just wanted to go into a little bit more detail here, what it's showing. So this is a geologic cross-section. What we're seeing is the earth in depth, and you can see at the top here, I think I have a pointer. At the top here you have a horizontal hydraulic fracturing well, which goes down into the earth and then turns into a horizontal orientation in order to pump down into the subsurface, fracture the rock in order to increase the permeability, and then we recover natural gas as well as some fluids. What's important here to remember is that these hydraulically fractured earthquakes are generally about a magnitude -2. So what Rick talked about before with the magnitude scale, you can actually get a negative earthquake magnitude because it's an exponential scale. So earthquake magnitudes don't stop at 0, they go lower than 0. What's important to remember with these very small minus magnitude earthquakes is that the actual size of a fault that slips is about the size of the table you're sitting at. It might move about 1/10 of a millimeter, and it's the same amount of energy as dropping a gallon of milk off of your kitchen counter. These are very small earthquakes. These are not the earthquakes we're talking about today. The earthquakes we're talking about today are much larger, have the potential to be felt, and have the potential to be damaging. Not to be too grim. They're manageable, so that's the point of my talk today. So in the case of wastewater disposal, you can see that there are 2 yellow wells that have been added to this, this figure here. And when you have fluid being disposed of in a sandstone body that has a sealing formation above and below in order to contain the hydrology and the pressure that may be accumulating there, generally, we don't see a lot of these larger triggered earthquakes. But in cases where you might be injecting fluid into a fractured medium that is in hydraulic communication with basement rock where larger faults may be located, that's when you start to experience an issue. So you may see a pressure perturbation buildup in these fractures. It communicates with the basement faults, and then because of normal tectonic stresses, the same stresses that drive natural earthquakes, we can trigger these events in an earthquake. So Rick also showed a figure very similar to this one. What you see on the x-axis is year, and then on the y-axis is the cumulative number of earthquakes of magnitude 3 and greater. This plot was made by Bill Ellsworth at the USGS, the Geological Survey for the US. And what you can see is that starting about 2001 and especially in about 2009, the number of magnitude 3 and greater earthquakes in the mid-continent really took off. And as Rick also said, there are now more magnitude 3 and greater earthquakes in the state of Oklahoma than there are in the state of California. And this, according to the, now officially according to the Oklahoma Geological Survey, they came out with a press release just last week. They are now attributing this increase in earthquakes to saltwater disposal, fluid injection. So that's why understanding how to manage this risk is important. So what I and my co-authors have done at the Stanford Center for Induced and Triggered Seismicity is come up with a guide that is aimed at giving regulators, oil and gas operators, and the public an understanding of what can go in, or what scientific principles should be considered, and how one might go about managing and mitigating risk associated with these earthquakes. This document is available online. It is freely available to anyone. You can just go onto our website, click to download, and you're set to go. What I'm going to be talking about today is a specific portion of that report. There's no way I could talk about the entire report here during this session. The beginning of the report focused specifically on site characterization, so that's understanding more of the geologic, hydrologic, geomechanical, and earthquake history, those types of topics that go into understanding a particular site and the hazards it may pose. And then we go into different recommendations on monitoring and reporting, injection practices, and monitoring and reporting earthquakes. And then we finish by talking about seismic hazard and assessing the risk associated with these earthquakes. And that's what I'll be talking about today. So here's a risk analysis workflow that we propose in this document. This workflow shows a lot of information right now, and I will be coming back to it frequently, so please don't feel like you need to digest it all at this moment. What's important to remember is that the site characterization component of this workflow is in the top, and I'll start by talking a little bit about that. So in order to do a risk assessment, we first need to consider the necessary factors. That includes the natural earthquake hazard in the area, or the likelihood that an earthquake might occur, or that you might experience a specific level of ground shaking, as well as the exposure. So that was the vulnerability component that I talked about before with natural earthquake hazard. In addition to that, we have a very unique portion of understanding risk for triggered and induced earthquakes, and that are what we call the operational factors. So the operational factors are the anthropogenic contribution to earthquake risk. These are things like injection practices, deciding what formation to inject into, and as well as other things that I will be discussing later. So first, let's just look at the natural hazard, or how the important information that one should consider when thinking about natural hazard. First is the geologic setting. So what do we know about the geology in the area, the particular formations, their porosity and permeability, or their ability to hold fluids and then allow those fluids to flow? As well as the earthquake history, so the frequencies of occurrence, sizes, and ground motions of the past events. Hydrologic properties, so you want to be able to understand how the fluid is going to flow once it gets into the subsurface, and whether or not there's a sealing formation, so a formation that has a very low porosity or permeability between the formation you're injecting into and the potentially dangerous faults that might be located in the crystalline basement rock. As well as the geomechanical state. So what's the state of stress in the area, as well as what faults are present and what are their orientations. So when we think about geomechanics, it's actually very important to consider the orientations of faults. And in order to understand how that impacts risk, we need to understand the state of stress. And again, I go into a considerably larger amount of detail in the document that's available online, and I encourage you to download it and browse through, send me an email, ask me any questions. I'd be more than happy to discuss it. So now the unique factor that goes into understanding risk for triggered and induced earthquakes are what we call the operational factors, as I said before. These are things like whether or not the injection horizon is in communication, hydraulic communication with the basement, so whether or not the pressure from the fluid can communicate to the basement, as well as what are the plans for injection rate, volume, and pressures. And then the operating experience in the area. So has operation occurred in the area before? Did you experience earthquakes? As well as, is there a cumulative effect that might occur because of the operating experience in the area? So if there are multiple wells injecting into one particular area, similar as what we're seeing in Oklahoma right now, perhaps that cumulative effect of pressure is causing earthquakes in the subsurface. And then, of course, it's important to consider the exposure. These are the communities we live in. These are the people we love. These are those that we serve. They're perhaps the most important component of this entire risk assessment. So you want to understand the total population and population density in areas around where you're injecting. You want to think about, are there hospitals, schools, and other critical facilities located there? What sorts of structures and infrastructure are there, roads, bridges, reservoirs, and to what engineering standards were they built? And of course, also thinking about the environment itself. Now we bring all of these together and we want to think about what is the tolerance for risk in a particular area. And you might be thinking, well, risk tolerance, what does that exactly mean? Well, every community, regulating body, and oil and gas company has a specific tolerance for ground shaking, and that is balanced with the potential economic benefit that you may receive from fluid injection. It's important to identify this tolerance for risk before doing the full risk assessment, because it could significantly impact the way you choose to operate in an area. And I want you to think about, just for a second, what you think your personal tolerance for risk might be. How often do you think you would be willing to feel the ground shake if it meant that there was an economic benefit in your community? It's a weird thing to think about. And it goes back to the fact that people have the potential to trigger earthquakes, and it is coupled with our development for energy in this country. Now back to our hazard and risk assessment workflow. So now that we've gone over the necessary factors that you need to consider, we want to start building this risk tolerance matrix, and this is the colored graph that you see here in the center. So bringing together all of these different factors, on the x-axis of this graph, we have the anthropogenic hazard, or the operational factors, and on the y-axis, we have the natural hazard. So what's important to think about here and understand is that the colors in this spectrum correspond to a traffic light system. So a traffic light system is a frequently used mitigation tool. So basically what you want to think about is if you find that your project itself lands in this green section of the risk tolerance matrix because of the level of the operational factors and the level of the natural hazard, then what you want to do is consider your actions based on the colors that you see in this graph. So if you find that your project is in the green area, then green means go, continue operating as originally planned within the laws or the regulations that are set. If you find that a project is within the amber section, then you may want to consider being cautious, or you can potentially reduce your operational factors or the impact of your operational factors to bring you further into the green section. And then if you find that your project is in the red portion of this risk tolerance matrix, perhaps you don't want to be injecting there. And it is important to recognize that there are parts of the world and the United States, and perhaps even parts of Colorado, that you flat out don't want to be injecting because of the exposure. You want to think about your communities. You don't want to potentially be triggering damaging events where there is a high exposure. And of course, those would be rare instances, very rare instances. So again, on the y-axis here, we have our operational, or on the x-axis here, we have our operational factors, and on the y-axis, we can think of this as shaking intensity. So it's going back to the natural hazards. And Rick did a really great job of explaining what the intensity scale is. So you can think about this y-axis as being the intensity scale, where if you find yourself down here, the hazard potentially being down here, where you're probably not going to feel an earthquake, even if very small ones are triggered, up to the top of this graph that I've made here, where you might experience strong shaking and damage could potentially occur. Something that's unique about this risk tolerance matrix that makes our work unique and our recommendation to all of you unique is that this matrix that we have constructed, it needs to be adjusted based on the tolerance for risk in the area. So the way I have it shown here is you can see there's considerable amount of green in this risk tolerance matrix, and then it goes into amber, and there's a really pretty small area for red. But what's noteworthy, so here's a higher risk tolerance, this is what I was showing you before, but what's noteworthy is if you have a lower tolerance for risk in an area, perhaps because the exposure is high, or maybe the community itself just doesn't really have the patience for ground shaking, then you might find that your risk tolerance matrix would look a little different, and the green section of this operational OK zone or operational go zone would be considerably smaller compared to other risk tolerance matrices. So going back to the workflow that we are suggesting, now that you have an understanding for the necessary factors that should be considered, the tolerance for risk in the area, as well as how the risk tolerance matrix would be populated in order to inform how you might go about managing the risk, now I want to talk to you about the traffic light system, which I mentioned very briefly before, but is something that has historically been used in order to manage and mitigate triggered and induced seismicity. But we're going to offer suggestions on ways to make it more proactive and less of a reactionary tool. So in a traffic light system, the way it's historically been used is you'll have magnitude thresholds or ground motion thresholds taking you from the green go operational zone up to the amber cautious zone and then into the red perhaps stop injecting or consider well abandonment zone. What we're suggesting here is that this can be a much more proactive earthquake management tool or earthquake mitigation tool. And the way that's done is by not just considering magnitude thresholds to go from each of these different zones, but also geologic observations. And this is where the importance of data comes in. So of course, geoscientists, geophysicists, earthquake seismologists can't do their work without data. And we actually know, maybe not as much as we would like, but a very considerable amount about the subsurface and how these earthquakes are being triggered. So without the data, we can't do our work. But what's important is there are geologic observations that may give us an idea of whether or not a larger triggered event could be coming in the future, in the very near future in some cases. So for instance, if we see very, very small earthquakes, perhaps magnitude 1, 0, or -1, start to move into the basement rock, if we're locating very small earthquakes moving into the basement rock, then it's entirely possible that those earthquakes and the pressure perturbation causing them is moving along a permeable pathway that is likely an active fault. So what we can do is by seeing these smaller earthquakes, ones that are generally not big enough to be considered for thresholds moving between these different zones in the traffic light system, we can use these smaller earthquakes to tell us whether or not there's actually a higher hazard in the area than we initially thought. And when that's the case, you might find yourself going from green to yellow, even though a felt event has not yet occurred. In addition, if you see these small earthquakes also lining up on a particular lineation, the event locations are starting to line up on what could be a fault, whether it's in the basement or not, that could help you move from green to amber to red. And again, the goal of all of this is not to shut down projects, but it's just to help inform the hazard in the area and to help you reassess how you might go about doing your injection practices and analyzing your risk in order to keep the project and the exposed population safe and happy. So in addition, if you start to see, all of these geologic observations, those are the types of things that can make a traffic light system more proactive and help you understand whether or not you can go from green to yellow, back down to green, just different combinations of mitigation using this tool. So again, as data is collected and as we start to understand more about the areas that we're injecting into, whether it be the hydrology, earthquake occurrence, or the locations of faults, you can use this information to reassess as you go through the life of an injection well. So it's not that you want to do a risk assessment once and then leave the well to be and let it, let the injection operations continue without any sort of further thought. What's important is that we reassess as we know more information, as we get more data, and frankly, as the tolerance for risk in a particular area changes. Sometimes a community might be on board until they feel an earthquake, and then after that, there's zero tolerance. So tolerance also changes as you go through this process. So in summary, to limit triggered earthquakes, more can be done. It's a lot of information. And of course, I'm coming from an academic standpoint and something that's perhaps a little less practical. I'm not the one going out and paying for monitoring. I'm not the one, trying to come up with regulations. So for me, it's easy to stand up here and say, okay, here's the science. Go forth and prosper. But that's not necessarily the case. You all have limitations, the communities have limitations, and I absolutely understand that. But there are ways that you can make this entire process more informed, more site-specific, more proactive, as well as tolerance-based. And I just want to leave you with a couple of reasonable priorities, or things that my being an academic, and of course, all of you have a much better understanding of what's reasonable. But here are the things that I think could be priorities for managing this, rather than trying to tackle the entire problem all at once. Here are a few good steps to start with. First is avoid injecting into formations that are in hydraulic communication with the basement rock. There are instances of projects either injecting directly into the basement and causing earthquakes, or projects injecting into formations that are lying directly on top of basement rock. And that's a huge issue right now in the state of Oklahoma. They're injecting into the Arbuckle, where they're trying to store a lot of salt water that needs to be disposed of. And that formation, the Arbuckle, is in hydraulic communication with large faults in the basement. That's where these larger events are generally thought to be coming from. In addition, try to perform site-specific risk assessments. The state of Colorado is doing a great job. I've looked through a lot of different regulations for different states in the US, as well as regulations for different countries, most of which are summarized in the report that I mentioned that's on our website. And the state of Colorado, I feel like, is doing a fantastic job. You try to think about where you're injecting. You want information on the earthquake history before you start injecting, and I think that's fantastic. It took me, this is just an example. You are all doing a great job of this already, but when I speak to other people, it took me 5 minutes to come up with this earthquake history map of the state of Colorado using publicly available data. It is not difficult to do these types of things. It's just a matter of getting the expertise involved and understanding that these things are available. And then, of course, just understanding in general the locations of potentially active faults. This takes quite a bit of data, but often there is data available that's out there that people don't know about or aren't familiar with. And then to finish, just utilizing a risk management program, something like the traffic light system, and something like the traffic light system we suggest that is more proactive. And with that, I'd like to leave it, and I thank you very much for your attention.